This is section 15.2 on acquiring an NMR spectrum. Instead of starting with our book this time, I like to start with a nice little resource for basic NMR spectroscopy, and that is this one by the Michigan State University Chemistry Department. So in general, we have some protons, and each of these protons has a magnetic spin that generates a magnetic field, either +1/2, shown here in this little video, or -1/2 in this little animated video here. We call those alpha or beta spin states. Now, each of these two spin states exists, but they are generally randomly associated in a molecule. You can't really find the difference in them unless you apply an external magnetic field. Once you do apply an external magnetic field, the difference in energy between the two spin states increases with the increasing magnetic field. This is a diagram showing that increase in energy, where in the beginning, with no magnetic field, you have no difference in energy, but as the magnetic field increases, this energy difference becomes very large. In fact, by increasing the magnetic field from 2 Tesla, which is not that strong, up to even 8 Tesla, you can see a huge difference in the spin energy of each. This means that it takes 360 times the energy to promote one spin state from alpha to beta at 8.46 Tesla, and at 2.34 Tesla, that same difference is only 100 times. So the interesting thing about NMR spectroscopy is that as you increase the magnetic field strength, you actually increase the resolution as well. And resolution means how easy it is to tell one peak or signal from another. This becomes very important because you can imagine if you have 2 signals that are very close to one another, you want to be able to tell the difference between them without any question. So in general, what we do in organic chemistry is we increase that magnetic field strength so that we can very easily tell the difference between 2 different and closely related signals. And in the previous section, 15.1, I mentioned that radio frequencies were going to be important. And that's because after we apply this magnetic field, the way that we find or that we irradiate these molecules to produce or to excite from one spin state to the other is through radio frequencies, because radio frequencies have the correct energy that we're looking for in promoting from beta to alpha spin state. So then what we need to talk about is how we actually take an NMR spectrum. So in your book, let's see, new share, vital source bookshelf, here we go. So in your book, it talks about a little bit about NMR spectrometers, and it shows you a fun little schematic cartoon of an NMR spectrometer. In general, you dissolve your organic material in a small amount of solvent, around 1 milliliter, and then you put them in a very narrow glass tube, and the glass tube is inserted in the top of this instrument. It comes down into the instrument in between a coil, which is a radio frequency generator. Let's see if we have yeah, I can show you a little diagram of that. Okay, here we are. The thin tube goes in between a coil that is the radio frequency receiver and the amplifier. Outside that coil, there's a transmitter that is irradiating the material with radio frequencies, and then there's a magnet on either side that is responsible for aligning the poles or aligning the spins of the molecules that are dissolved in the solution. And once this happens, there will be a sweep in the spectrum that is where we look for the NMR signals. And what we're looking for is what types of radio frequencies these molecules absorb. Because if you know the energy difference of where the spin state should be, you can then calculate how much energy they should be absorbing. And if you sweep over several frequencies, you can find the spectrum, the spectrum the signals that you are looking for. So let's see, let's go back to the Vital Source bookshelf. Here we go. Okay, so you can actually acquire one of these samples or one of these spectra in 1 to 2 seconds, and you end up averaging the spectral signals over many, perhaps even hundreds, in order to get an average signal that tells you with high accuracy and precision what molecules are in the solution. And to prepare the samples, you generally dissolve them in a solvent of highly deuterated molecules like chloroform D here, where the hydrogen is replaced with a deuterium, acetonitrile D3, or benzene D6. Notice that the name of the deuterated material tells you how many deuteriums have been incorporated into the molecule, except for deuterium oxide. Deuterium oxide is special. We don't call it water D2, we call it deuterium oxide. So these solvents are important because deuteriums do not have any resonances in NMR spectra. They are not NMR active because they don't have an odd number of protons or neutrons. So because it's 2, they are NMR inactive, and this allows us to see only our molecules. And that's important because even at very high concentrations, the amount of solvent that are present in an NMR tube is much, much higher than the molecules we're looking for. So we have to be sure to use deuterated solvents in order to have enough signal from the molecules that we're interested in. And using this technique, as you'll see, we're going to be able to tell a lot of very good structural features about our molecules. So this was section 15.2.